In this lesson, we're going to be working on graphing quadratics in standard form. We completed some of these notes on Friday in class, but I just wanted to give you a chance to look back over them and get your brain thinking again. So this first problem we did together, we factored the function y equals x squared minus 2x minus 3 using the skills that we learned in our factoring unit. We found two factors of negative 3 that add up to negative 2, and we put those numbers into parentheses as binomial quantities. These two quantities would multiply back together to give you the original function. Then we discussed the zeros and the fact that the zeros are the opposites of the numbers inside the factors. We could solve them by setting each one equal to 0. X plus 1 equals 0. We would subtract 1 from both sides to get negative 1. And we would add 3 to both sides to get positive 3. It opens up because the leading coefficient is positive 1. And we did a little sketch where we showed the zeros on the x-axis and a parabola opening upward. Then we discussed the fact that the axis of symmetry is halfway between any pair of points that are aligned horizontally on the graph. So we counted to find the point between, exactly between negative 1 and positive 3 on the graph. And that's just a bit of a recap of the things that we learned in previous units that are going to help us as we move forward with graphing. The leading coefficient in a quadratic function serves the same purpose whether you're working in standard form or in vertex form. A tells us whether the graph opens up or down, and also whether there is a dilation, a stretch or a shrink. In standard form, the y-intercept is also evident by the constant of the function. We're going to use this little equation x equals opposite b over 2a to find the axis of symmetry for our function and the x-coordinate of our vertex. We need to identify the values for a, b, and c and substitute them into the equation. We have negative 2 on the top and 2 times 1 on the bottom, which simplifies to negative 1. So the x-coordinate of our vertex will be 1, and the axis of symmetry will be the vertical line x equals 1. Now we'll substitute this x value that we just found back into the original function to solve for the y-coordinate of the vertex. Now you're ready to practice identifying the vertex and axis of symmetry for your graphs. We're going to substitute the values for a, b, and c into x equals opposite b over 2a to find the axis of symmetry and x-coordinate of our vertex. Then we'll substitute this x value back into the function to find the y-coordinate of the vertex. We'll also look at the value of a to determine that the graph opens up because the value of a is positive. In standard form, 0c also represents the y-intercept. So if we identify the value of c for this function, and c is 2, then the y-intercept, or the point where the graph crosses the y-axis, is 0, 2. Pause the video while you try practice problems 2, 3, and 4. Now we're ready to begin graphing quadratic functions in standard form. The steps for graphing are listed at the top of your page. If you get stuck on a problem, just look back and follow along with those steps. So in example 2, we're working with y equals x squared minus 2x minus 1. The first thing we're going to do is identify the values for a, b, and c. Then we'll substitute b and a into the equation x equals opposite b over 2a to identify our axis of symmetry and the x-coordinate of our vertex. Next, we'll substitute this x value into the original function to determine the y-coordinate of our vertex. The vertex will be at the center of our graph, and also it will lie on the axis of symmetry. I've plotted the point 1, negative 2, and now I'm ready to start graphing the rest of the function. We're going to follow the pattern of the parent function y equals x squared. The vertex will be represented by 0, 0, and the other ordered pairs will represent moves away from the vertex on the right and the left of the vertex. So after I plot the vertex at 1, negative 2, that represents 0, 0, I'll move to the right 1 unit and up 1 unit, and then I'll place my pen back at the vertex and move to the right 2 units and up 4 units. After that, I'll move to the right 3 and up 9. Once I've completed the right side of the graph, I'll reflect it across the axis of symmetry to complete the other half of the graph. Now that I'm finished graphing, I can complete the table for the function. These points are different than the 0, 0, 1, 1, 2, 4 pattern of the parent function because these ordered pairs represent the actual locations of the points on the graph of y equals x squared minus 2x minus 1. If you're feeling confident, you can pause the video here and try examples 3 and 4 on your own. Something important to note about example 3 is that the leading coefficient is positive 3. This means that the graph will open upward when you begin plotting your points, and that it will have a stretch by 3 units. All of the y values will grow 3 times as fast as you move away from the vertex. So as I begin plotting, the y values are going to go up 3 times as much. So as I move to the right from the vertex 1 unit, I'm going to go up 3 units. And as I move to the right 2 units, I'm going to go up 12 units. Then we'll reflect both of these points to the other side of the axis of symmetry to complete the graph. After finding the axis of symmetry and the vertex for example 4, we'll go to the right 1 and up 2 because this has a stretch by 2. We'll reflect this to the other side. The next point would be 8 units above the vertex, which does not fit on the graph. So as I'm completing the table, I'll name the points 1, 5 and 2, 11, which is 8 units above the vertex. Example 5 has a reflection, which means the graph opens down. This is because the value of a is negative. After we plot our vertex, we'll go to the right 1 and down 1, and then to the right 2 and down 4. Reflect these to the other side of the axis of symmetry to complete the graph. Now you should be ready to practice on page 24 and 25 of your packet.